All right. So we're gonna have to start this over. I realized that I don't know, somehow the thing got muted. Anyway, we're gonna start it over. So this is our live lecture for week 2, Friday, for applied statistics. My intent is for this video to be, pre-recorded, so that way you all as my students can watch it at your leisure. There it is. Okay. Let me turn this down. So you can watch it at your leisure, and I do intend to be available during class time for questions. Today we'd just like to go through sections 2.4 and 2.5. Let's see. A few notes for the students. Exam 1 is available on Pearson. As a result of all of the social climate that's going on with, the main thing that everybody's experiencing right now, the reason that we have to do all this. The online learning companies like Pearson and Cengage and different companies like this are offering full complimentary full access to their services. So if you're one of my students and you're having trouble gaining access, just reach out to me and we'll get you set up. But currently I'm only accepting assignments via Pearson. So you just do the assignments on Pearson. We have exam 1 available on Pearson and we have quizzes there. Okay. Also, as you watch these videos, it's a good idea to take notes as if you're in class. One, go ahead and be subscribed to my YouTube channel, and make sure your notifications are turned on, because this is going to be my main mode of communicating. So as I post videos, I try to make a relevant title, so that way you can see if the video I'm posting might be pertinent to you or not, or relevant to you, and that's how we're going to proceed. Also, as you watch this video, watch the video, take notes as if you're in class. As questions arise or you think of questions, write them down, and you have to either email me, be present during the actual class time, or attend my virtual online office hours, or just email me. Any of that stuff will work. Or you can actually call my office phone. Those calls are being forwarded, so those calls get through currently as well. But just reach out and we'll make sure to walk you through and kind of get you set up and on the path that we need to be on. So everything looks healthy. I think that everything is kind of working properly. So I'm going to go ahead and move forward with these presentations. Again, we want to do 2 sections today, and the first section that we'd like to get through, we're continuing with chapter 2. So exam 1 is over chapter 1. It's only like 3 sections, and the sections are really short. So just make sure to kind of get it done. Again, exam 1 is available on Pearson, and it's due in a couple of days. It's due this Saturday by 11:59 p.m. Okay, so I think I put it up like last night. So and I think usually when I post stuff like that, I'll post an announcement in our Moodle page. So what that means is that be sure that your GMC emails are being forwarded to an email that you check regularly. So that way, as I make these announcements, you get them to your email, and you should definitely be having notifications on your device or checking these things regularly. Okay, I can't think of anything else, so let's keep moving. So today we're going to look into section 2.4, measures of variation. Okay, so we're just going to continue with these ideas. Some objectives here are how to find the range of a data set, how to find the variance and standard deviation of a population and of a sample, how to use the empirical rule and Chebyshev's theorem to interpret standard deviation, how to approximate the sample standard deviation for group data, how to use the coefficient of variation, and let's do it this way so that's not blocking. How to use the coefficient of variation to compare variation in different data sets. Okay. Did I skip something? No. Okay. So the range of data is going to be the difference between the maximum and minimum data entries in the set. The data must be quantitative. So the range is basically the max minus the min. So for example, we have 2 corporations, each hired 10 graduates. The starting salaries for each graduate are shown. We're asked to find the range of the starting salaries for corporation A. So this data is in thousands of dollars. So we have 41,000, 38,000, so on and so on. So if we want the range, we want the max minus the min. As we kind of scan, we got 41, 45, 47. Looks like 47 is the max, and it looks like 37 might be the min right here. So 47. So then the range is basically 47 minus 37. So the range for that data set should be 10,000. Okay, so we see. So the note suggests to ordering the data helps to find the least and greatest salaries. We see the max is the 47 and the minimum is the 37. So the range is going to be our 10,000. Okay. So both data sets in the last example have an average of 41.5 or 41,500, a median of 41,000, and a mode of 41,000. And yet these two sets differ significantly. The difference is that the entries in the second set have a greater variation, as we can see in the figures on the next slide. The starting salaries for Corporation B are more spread out than those of Corporation A. So variation essentially is a discussion on how spread out our data is. So you see in these two examples, they had the same, I think it was, what did we just say? Both data sets have an average of 41,500, a median of 41,000, and a mode. So even though they have the same central tendency, the second data set was more spread out than the first, right? So it's a larger range, right? So variation is a discussion on how spread out the data is. So deviation is going to be the difference between each entry and the average of the data set. So if you think about the word deviation, deviate means like how far away you are from something. To deviate from, like, you know, if you're on the straight and narrow course, if we're on the straight and narrow course, if we're deviating from the straight and narrow course, then we're kind of going off to one side or the other. In context, this essentially is a similar notion or idea. Deviation is the difference between each entry and the average of the data set. So if we have a population data set, the deviation of each x is going to be x minus mu. Again, this is mu, Greek letter mu. This just means population average. The deviation from a sample set is going to be each entry minus the sample average, x bar. Okay. So then population variance, again, to get a sense of how spread out the data is, the larger the variance, the more spread out the data is. Population variance is going to be given by this. We're going to say each x minus the average, then we're going to square those results, add those up, and divide by the total number of entries in the population. And that's what we're going to mean by population variance. And then to find the standard deviation, we're basically just going to take the square root of the variance. So this line down here is just a square root of the above line. Standard deviation tells us how far away from the center, from the average we are. Variance tells us how spread out the data is. Okay, so that's the context of those two notions or ideas. So some observations about standard deviation. The standard deviation measures the variation of the data set about the average and has the same units of measure as the data set. The standard deviation is always greater than or equal to 0. When sigma is 0, or when the standard deviation is 0, the data set has no variation at all, and the entries have the same value. As the entries get further and further away from the average, this means that it's more spread out. The value of the standard deviation, or sigma, increases. So that's lowercase sigma, which we're going to use for a standard deviation. Okay. I'm going to let you go through this on, let me see, finding population variance and standard deviation. I'm going to let you read through. Actually, let me kind of explain some of this stuff. So so find the average of the population set. So remember, just like average in a normal sense, we add up our entries divided by the total number of entries. So this is mu is going to be the average of our population. We add up our entries divided by the total number of entries, and that'll give us the population average. Find the deviation of each entry. We're going to say each x minus the average. Okay, so each x minus the population average. And then we're going to square each deviation. These are just steps on how to find the population variance and standard deviation. And then we want to add to get the sum of the squares. So once we square each entry, we're going to add those up. We're going to call that result the sum of the squares. Then we're going to divide by the number of entries in the population, capital N, and that'll give us the population variance. And then for the population standard deviation, we're going to take the square root of that result. Okay. Moving along. Oh, shoot. Okay, find the population variance and standard deviation of the starting salaries of Corporation A listed in the first example. Okay, I think I can do this from memory, except for the data. Can I see the data? Okay. Well, I guess we'll just use this. This will probably be simpler than doing it by hand. So for the data, we had 10 entries and the sum of all the x's came up to 415. So that means the population average is going to be the 415 divided by 10, which is going to be the 41.5, right? So first we found our average of the population. Next, we wanted the deviation for each x, for each entry. So we took each entry minus the average, and we get this list here. We get this list on the right-hand side. Then what we want to do is square those entries. So we're going to say negative 0.5 squared. We're going to square each of those, right? Here. So you see the negative 0.5 squared, we get this. So this is each of those entries squared. Then we want to take the sum of the squares. So we want to add all those up and we get this, right? Okay. So we have our sum of squares. So then for the variance, basically what we do is we take the sum of the squares divided by our big N, and we get that the population variance is 8.9. Okay. I think that's what, 1,000, so 8,900? Because it has the same units as the data set. And then the population standard deviation is 3. So it says the population variance is 8.9 and the standard deviation is about 3 or 3,000, right? So 8.9 is going to be 8,900. That's how spread out the data is. Okay. I think this is okay. Approximately, right? Right here. Because I thought the range was 10,000, right? So anyway, the population variance is approximately 8.9. And so the spread is about 8.9. Okay. Let's keep going. So that was a discussion on population variance and standard deviation. Now, I'm not, I will be honest, this thing here, I'm not sure where this extra -1 comes from, but the sample variance is essentially the same as population variance. You're going to say each entry minus the average of the sample in this case. Take the sum of the squares. And instead of dividing by n, we're dividing by n-1. Now, I'm not really sure where the -1 comes from. I haven't figured that part out yet, but this is what we're using for sample variance. And then once we have the sample variance, then we just take the square root of the variance to get the sample standard deviation, right? So this comes in for the sample standard deviation. Let's keep it moving. So then this is essentially a repeat of the same way we did the population variance and standard deviation. It's similar, just we have to adjust for it to be a sample instead of a population. So first find the average of the sample data set. So add up our entries divided by the number of entries in the sample. Find the standard deviation. So we're going to say each entry minus the average, the sample average. We're going to square each deviation. So we're going to basically, those results, we're going to square them. And then we're going to take the sum of the squares. And it's essentially the same. Then we're going to take the sum of the squares divided by n-1. And then that'll give us a sample variance. And for the sample standard deviation, we take the square root of the sample variance. Okay. So in this example, in a study of how, it says finding the variance, the sample variance and standard deviation. In a study of high school football players that suffer concussions, researchers placed the players in 2 groups. Players that recovered from the concussions in 14 days or less were placed in group 1. Those that took more than 14 days were placed in group 2. The recovery time in days for group 1 are listed below. Find the sample variance and standard deviation of the recovery times. Okay. So I feel inclined, I want to do this one, just from scratch without the notes. I just want to see if I can do it, right? Just to have a little bit of fun. So what I'm going to do, I'm going to add a page and see, can I do it with minimal support? Okay, now keep in mind with the structure that we have, obviously you can use support. The real thing is just to see, can you, get to the conclusion, right? But I'm going to give this one a go. So we're asked to find the sample variance and the standard deviation. So first let's start with finding the average, right? So let me see. Let me just kind of go back really quickly. Yeah, the sample variance, right? So I'm going to say the variance, and actually I usually like to do like this, paper. Let's do some grid paper. So we're going to say the variance, tag on it. This is fun. I'm going to say sample variance. Let's see, that should be, we're going to say each x minus the sample average x minus, it's going to square those. I'm just doing the formula off the top of my head. But you could you don't have to do that. You can just look it up. So each x, we're going to find the deviation. So each x minus x bar, square those results, add them up, and then we're going to divide by, instead of dividing by n, we're going to divide by n minus 1. That's for the sample variance. And this is going to be our s squared. All right. And then for the sample standard deviation, I think for the sample, something like that, is going to be basically the square root of s squared, which is basically going to be the square root of this thing here. I think this is correct. I'm going to go with it. Copy, paste. Okay. So I usually like to kind of do this in a chart. I'm going to use this. Oh, that's a little bit. Let's do this color. It's a little bit better. So first we're going to start with each x, right? So we have 4. Let me see, I can go like this, I guess. We have, let's just do it like this. Okay. So we have 4, 7, 6, 7, 9, 5, 8, 10, 9, 8, 7, and 10. Okay. See if I can do like that. Let's shrink this down just a little bit. All right, so let's kind of align it like this, right? Okay. And I'm going to make this a little bit smaller. It's a little thick for me. Okay. And one other thing. Let's just move it like this, right? I'm just trying to get my alignment and organization a little bit better. That's all. We'll put the X there. The 4 can go like there. It'll be the 7. Is that too much space? I don't think I have enough space for what I want to do. Let's try it like this. Hopefully it's not too jumbled. I feel like it's too jumbled. Okay, this will work. Yeah, sorry about that. Yeah, I wanted to be a little bit spaced out, but I was kind of running out of space. Okay. So that's the first thing. We have each x. So then and let's go ahead and find our x bar. I'll do that in green. So if we're going to do x bar, we have to do what? Basically sum up our x's. So the sum of the x's divided by little n, right? So let's see. 7 and 4 is 11. Plus 6 is 17. Plus 7 is 24. Then we have 33, 38, 46, 56, 56, 65, 65, 73, 80, 90. I think that's 90 divided by, we have, let me see, 2, 4, 6, 8, 10, 12. Let's see, divided by 12. Let's just do like this. This might be a little bit better. No, cancel. Okay, I'm just gonna kind of confirm my numbers instead of trying to do it off the head. Okay, so we're gonna say, let's do parentheses. Let's just do this. 4 plus 7 plus 6 plus 7 plus 9 plus 5 plus 8 plus 10 plus 9 plus 8 plus 7 plus 10. All right, should be 90. Okay, and then it looks like we have, I think we counted 12, right? So we're going to say divided by 12, 7.5. Okay, let's just go with it. So this is going to be 7.5. Okay, so let's see. Okay, so the next thing that we want to do is x minus x bar for each entry, right? So we're going to say 4 minus 7.5, right? We're going to say 7 minus 7.5, 6 minus 7.5, 7 minus 7.5, 9 minus 7.5, that's a 9, 5 minus 7.5, 8 minus 7.5, 10 minus 7.5, 9 minus 7.5, 8 minus 7.5, 7 minus 7.5, and 10 minus 7.5. So if we calculate those, let me see. This one's going to be negative 3.5, negative 0.5, negative 1.5, negative 0.5, not negative, 1.5 for this one, negative 2.5, 1.5, sorry, that's not 1.5, that's just 0.5. 2.5, 1.5, 0.5, negative 0.5, 2.5. Okay, so we say each x minus x bar, right? We get this. Okay, so then we want to square those results. So we want to say the next thing is the x minus x bar, each of those squared. What's 3.5 squared? 12.25. So this one is 12.25. This is 0.25 plus 2.25 0.25, 2.25, I think that's a 6.25. Okay. 0.25, 6.25, 2.25, 0.25, 0.25, and 6.25. Okay, so we squared each of those entries. All right. So then here, what we want to do is add them up. So if we add up these results, let's do it here. We're going to say 12.25 plus 0.25 plus 2.25 plus 0.25 plus 2.25, 6.25, 0.25, 6.25, 2.25, 0.25, 0.25. And hopefully I got my keystrokes proper. Okay, let's see how 39. Is that correct? Let me look. So 3, I think that's the only one that's 3, right? Okay. We should have what, 12 entries? Let me see. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. And then 12.25. I'm just going to go with it. Hopefully we got it right. Okay. And we got a result again of 39. Okay. So those add up to 39. Now I know we're doing this manually. I'm just showing that it's possible. Now obviously there's software that does all this stuff quick for you and things of that nature. So then the variance, the sample variance, the variance of the sample is it should be that 39 divided by 12 minus 1. And then let's see, we're going to say that answer divided by 11. 3.5 approximately. Okay. That's the sample variance. And then for the sample standard deviation is going to be the square root of the sample variance, which is going to be the square root of 3.5, which is approximately. What I'm going to do, I'm going to hit square roots of that answer. 1.88. I'm just going to say approximately 1.88. It's the standard deviation. Okay, so we got this for our variance. We got this for our sample standard deviation. Okay, let's see, how do we do? That was fun. 3.5 and 1.88. Let's see, how do we do? So the 39 is there. You can see the numbers. They add up to 90. This looks good. 3.5. And we got 1.88, which is approximately 1.9. Okay. Okay, and the units here are days. Okay, so again, sample variance and sample standard deviation have the same units as the data set. Okay, that was fun. Moving along. So sample, we could actually use technology to find the standard deviation. It says sample office rental rates in dollars per square foot for Los Angeles are shown in the table. Use technology to find the average rental rate and the sample standard deviation. We got to put in the data. We could find the average. Let me see. I'm just going to show it here. So this can actually be done. Let's see if we can do it on our TI-84 Plus. Okay, let's go back to our data. Let's pull up our data and see. Let's try if we can get it in this calculator. All right. So what we're going to do, you see the orange second button and the teal green alpha button. To the right of the green, it says stat. I'm going to click on that button that says stat. I'm going to go to edit. And I'm going to type in all this data, right? So we have 51. Let's go 47, 33, 74, 24, 36, 41, 42. I'm going to go 30. 14, 11, 42, 40, 22, 35, 29, 15, 87, almost missed that 7, 35, 51, 26, 40, 36, and 24. Okay. So we have our data in there. Let's see. If we go, I'm going to quit. And then if we go, I'm I'm gonna go back to stat. I'm gonna go to calculate. Let's see. The question asks for the average. Let me see. Let's see. Okay, so we want to see, can we create this data? One very stat. Yeah, so number one, right? So if we hit number one, we hit enter, variable one number stat. You see we get to the 36.875. So that's the sample average, okay? The data, the entries added up. We have the sum of the squares. Let me see. We got the sample average, the sample standard deviation, so on and so on. So you see it there, okay? So all we did was type in the data, and then we went back to stat and go over to edit, go over to calculate, and it just spits out the answer, okay? All right, so we're gonna let that be. All right, I'm watching the clock. I kind of do have about like 30 minutes remaining. There was another section that I want to get through. I think I'm going to go ahead and kind of keep going with my usual rhythm. But yeah, we'll just kind of keep going. I wish I had the time that I've been streaming. I'm pretty sure that's located somewhere. I just don't know where it is. I'm not going to worry about it. So let's keep moving. Interpreting standard deviation. Standard deviation is a measure of the typical amount of entry deviates from the average. The more the entries are spread out, the greater the standard deviation. Okay, so like in this first example, the average is 5, but the standard deviation is 0. So the data is not spread out. It's all the same. It's all right here in the center. Notice in the second example, the average is still 5, but the standard deviation is 1.2. So it's a little bit more spread out. Here, the average is still 5, but now the standard deviation is 3, so the data is even more spread out. Okay. So without calculate, estimate the population standard deviation of each population standard deviation. So how far away from the average? Okay, so the first one should be 0 because the data is not spread out at all. If the average is 4, what is this, like 1? It's spread out by a unit of 1 from the center. Let me look at it. 0. Let's look at it. So we got the 0, fine. This one is 1. I think we got that one as well. Okay, so it says each of the 8 entries has a deviation of plus or minus 1 or plus or minus 3. So the population standard deviation will be about 2. Okay, so about 2. So here's the average. This one's plus 1. This one's plus 3. So the average between 1 and 3 is 2. That makes sense. By calculating, we can see that this is greater. That something, I think the symbol might be missing, is greater than 2 with a standard deviation of 2.2. Okay, that's fine. Let's see. Let's kind of keep moving. We got a lot of slides. Let's see. Interpreting standard deviation, empirical rule. Oh, so we have the 68, 95, 99.7 rule. For data with a symmetric bell-shaped distribution, the standard deviation has the following characteristics. About 68% of the data lie within 1 standard deviation of the average. 95% of the data lies within 2 standard deviations, and about 99.7 lie within 3 standard deviations. So when our data has this bell-shaped curve like this, then as long as we're plus or minus 1 standard deviation, that's going to be about 66% of the data. 2 standard deviations is going to encompass about 95% of the data, and 3 standard deviations is going to be about 99.7% of the data, right? Okay, so in this example, it says in a survey conducted by the National Center for Health Statistics, the sample average height of women in the U.S. was 64.2 inches, with a sample standard deviation of this. Estimate the percent of women of those heights that are between 58.4 inches and 64.2. So if we're going to use the empirical rule, we do have that we are using that this data is going to be a bell-shaped curve. Let me see. So it says the distribution of women heights is shown. Because the distribution is bell-shaped, we can use the empirical rule. So the average height was 64.2, that was given, which is here. So then the question asks, estimate the percent of the women who are between 58.4 and 64.2. So if the average was this, and it had a standard deviation of, what was it? The standard deviation of 2.9 inches. So we have our average, and then we're going to say plus 2.9, plus 2.9, plus 2.9, and minus 2.9, minus, minus, minus. So each step is 2.9 inches. So then the question said, what percent of the women are between 58.4 and 64.2? Well, this region is 34. These two together are like the 68. So this was the 34.13%. This one is going to be 13.59%. So then we add those two together, right? But it's coming out of this notion here. This is about 34%, 13.5. So these two together, 34, 44, 47.5. Percent, right? Where is it? Here it is. So there's 47. So about 47. Remember we said 47.5. So about 47.72% of the women are between these, right? Okay, we're gonna let that be. So forgive me if I pronounce this incorrectly. Chebyshev's theorem: the portion of any data set lying within k standard deviations, as long as k is greater than 1, is at least, of the average, is at least this. So the percent, right? If k is 2 in any data set, at least 75% of the data is within 2 standard deviations. And when k is 3, again, 3 standard deviations in the data set, at least 88.9% of the data lies within 3 standard deviation of the average. Okay. Let's see. So it says the age distributions for Georgia and Iowa are shown in the histograms. Apply Chebyshev's theorem to the data for Georgia using k equals 2. What can we conclude? So it says when k is 2, about 75% of the data is within 2 standard deviations. So we have our average here and we have our standard deviation. So about 75% of the residents are, I think it's like 80, right? The average, where is it? Where's our mu? The average is here. So 2 standard deviations. Now, if we say, what's that going to be? 44.6. If we add 44.6 to this, let's just do this really quickly. So let's quit this or clear. So it says that 75% of the data is going to be within 2 standard deviations, or at least. So then if we say that 37.3 plus 2 times 22.3, we get up to like about 82. And then I think if we say minus, it goes into the negative. So we have to just go to 0. If we say minus here, it'll go 2 standard deviations to the left. We're at negative. So we're not going to do a negative age. So we're saying that so what this means, if we have our average age and 2 standard deviations, what is this chart telling us? Population. About 75% of the population of Georgia is going to be between 0 to 80. I think that's what this means. Let's look at it. So if we go 2 standard deviations to the left, we get the negative 7.3. We have to use 0 because ages can't be negative. If we go 2 standard deviations to the right, we get this 81.9. So we can say that at least 75% of the population of Georgia is between 0 and 81.9 years old. Okay. Also, an age of 100 lies more than 2 standard deviations, so this age is unusual. Okay. Let's keep it going. We're about halfway through this. I wish I could see stream time, but I'm not going to worry about it. Let's kind of keep moving. So sample standard deviation for a frequency distribution. Okay, so if you think about the frequency distribution is going to tell us the frequency of each entry. So whereas before we didn't have the frequency here, we were actually doing each entry individually. Whereas now we're going to have multiples of each entry. So to account for that, we're going to multiply by the frequency of each entry. Okay, the number of entries in each data set. Okay. For the sake of time, I'm just going to kind of go forward. So we collect random sample of the number of children per household in the region, find the sample average and the sample standard deviation of the data set. So instead of, we will still find the sample average and things of that nature, but instead of doing it for each entry, we're going to use the frequency. So we're going to go through and see how many 1s do we have, how many 3s do we have. And so when we do that, we have our data entries X, right? And we have the frequency of each one, so how often each one occurs, right? So then each entry times its frequency means that we have this, it's going to be this. Let me see. So they were like, this happened 0 times or whatever. Then this one happened 19 times. This one's 14, So each entry times its frequency. So then the sum of the frequencies gives us this. So if we want to find the average, so if we want to find the average, instead of adding all of these up, instead of saying 1 plus 1 plus 1 plus 1, we can say what? Okay, we had 19 ones. So we could say 1 times 19 gives us this, 0 times 10 gives us this, 2 times 7 gives us this. So we have all of these entries, and then we add them up. This is going to be the same as if we just added all these entries. They're going to add up to 91. And then we're going to say that divided by, we have a total of, let me see, 2, 4, 6, 8, 10 rows, 2, 4, 5 columns. So there's 50 entries. So then the sum of the frequencies, we have again 50 entries. So then 91 divided by 50. So the sample average is about 1.8 children. Then we want to take that and use that to find the sample standard deviation. So we take each entry, we factor in the frequency. We're going to say each x minus the average, right? So each x minus the average will get these results. We're going to square each of those entries, and then we need to factor in how often each of these occurred. So this occurred 10 times, so that's why they say this times 10 to give us this. This one occurred 19 times, so we're going to say that times 19. We do that for each one. We take the sum of the squares, and we get this, right? And then we're going to say this divided by n minus 1 for the sample standard deviation and take the square root. And we get this, okay? I'm going a little bit fast because I'm a little bit short on time, and I'm doing my best to honor the time. But I'd still like to get to the slides, okay? If anything is not clear, don't hesitate to reach out. Email me. You can call my office phone, and we can talk about it, okay? I'm going to shut this down. All right. I think I'm actually going to, because of the sake of time, I'm going to leave this as an exercise. Okay. So just give it a go and let me know if you need support with it. I'm going to let you work that one on your own. I'm just going to kind of go to the next part because I really want to get onto the next section. Okay. So yeah, I'm going to leave that last example up as an exercise for you. Let's take some time to actually go ahead into the next section, and we're going to move into section 2.5, measures of position. Okay. Got 30 slides. Hopefully, I don't know, we'll see how it goes. Some objectives here are how to find the first, second, and third quartiles of a data set, how to find and interpret the interquartile range of a data set, and how to represent a data set graphically using a box and whisker plot. Also, we want to look at how to interpret other fractals such as percentiles and how to find percentiles for a specific data entry and determine and interpret the standard Z-score. Okay. So fractals are going to be numbers that partition or divide an ordered data set into equal parts. Quartiles approximately divide an ordered set into 4 equal parts. The first quartile, about 1/4 of the data set fall on or below quartile 1. About half the data set fall on or below Q2, which is our second quartile, which is the median. And then the third quartile, Q3, about 3/4 of the data set fall on or below Q3, right? So we have the solution and we are short on time, so we're going to let it be. It says each year in the U.S., automobile commuters waste fuel due to traffic congestion. The amounts in gallons per year of fuel wasted by commuters in the 15 largest U.S. urban areas are listed. Find the first, second, and third quartiles of the data set. What do we observe? So we have this data. First, I think we want to put the data in order, right? We want to put it in order, so from smallest to largest. And then once we have it in smallest to largest, first we find the median, right? So let me see, we have 2, 4, 6, 8, 10, 12, 14, 15. We have an odd number of data entries, right? So that means the middle entry is going to be our median. So this is going to be our Q2. Then if we cut that in half, so if there were 15, so this is entry number 8. Cut that in half, we go to entry number 4 for Q1. 1, 2, 3, 4. So this is going to be Q1, and then we go 4 from 8 to get to Q3. 1, 2, 3, 4, right? To get Q3. So then now we have our Q1, Q2, and Q3. And we have that. I'm going to let that be. So it says its tuition costs in thousands for 25 liberal arts colleges are listed. Use technology to find the first, second, and third quartiles. What do we observe? So again, we would type this into, we can use the 84 plus, type it in, and we can actually generate these. It's similar to how we did the last one, right? So we see here for 84 plus, again, it's still the one variable stat or whatever, one var stat. So we do the same thing, type the data in, and we just have to scroll down, and then it'll give us Q1, Q2, and Q3. And it gives us the max and the min. That's actually kind of cool. Okay, I'm going to let that be for the sake of time. I am running a little bit short on time, but I don't think we have that many slides, and they actually go fairly quickly. So the interquartile range, the IQR, is going to be the measure of the variation that gives the range of the middle portion of the data, or about half of the data in the middle. The difference between is basically the difference between the third and the first quartile. So the interquartile range is going to be Q3 to Q1. All right. So we're going to let this be. I mean, it's not too bad. I don't mind showing it. So we're asked to find the interquartile range from the first example. Are there any outliers? So we had that Q1 was 23 and Q3 was 30. So then IQR is going to be 7. To identify any outliers, first note that 1.5 times the IQR is going to be 10.5, right? There is a data entry 11 that is, let me see, there is a data entry 11 that is less than Q1 minus 1.5 times this. Let me see. So if we take, let me think about this. So we're talking about outliers, right? So identify any outliers. First note that 1.5 times IQR is going to be this. All right, okay, that's fine. So then if we take Q1 minus that 1.5 times IQR, so we say the 23 minus 10.5, we get 12.5. So because the 11 is less than this 12.5, it's going to be considered an outlier. And if we take Q3 plus that 1.5 times IQR, we get the 40.5. We don't have any entries beyond the 40.5, so there's no entry outliers going to the right. But we do consider the 11 because it's less than this whole Q1 minus 1.5 times IQR. So the 11 is considered an outlier. I think when we look at the box and whisker plot, that'll kind of help with all of that. Okay, we're going to let that be. So the box and whisker plot, it's an exploratory data analysis tool. It highlights important features of a data set. It requires it's a 5-number survey. We have the minimum entry, the Q1, Q2, and Q3, and then the maximum entry. All right. So to construct a box and whisker, I find the 5 numbers, minimum, Q1, Q2, Q3, and the max. Construct a horizontal scale that spans the range of the data. So we do a bar that goes that spans the range. We want to plot the 5 numbers above the horizontal scale. Draw a box above the horizontal scale, basically the IQR, and draw a vertical line in the box of Q2. Draw whiskers from the box to the min and maximum entries, right? So we have this. Let me see, I'm watching the clock. We have our minimum entry, Q1, Q2, and Q3, and then our max. So Q1 was here. We have our horizontal bar that spans the data. We have our minimum. We have our max. Here's our Q1. Here's our Q2 and Q3. We do a box going from Q1 to Q3 with a vertical bar through Q2. And then we draw whiskers from Q3 to the max and the min. All right. The box represents about half the data, which are between 23 and 30. Now it says the left whisker represents about a quarter of the data, so about 25% of the data is less than 23. The right whisker represents about 1/3. The right whisker represents about 1/3 of the data, so about 25% of the data entries are greater than 30. Also, the length of the left whisker is much longer than the right one. This indicates that the data set has a possible outlier to the left, right? possible outlier to the left. Now we could confirm it if we did the whole 1.5. If we said Q1 minus 1.5 times IQR, and see if there are any. Yeah, they're 11, right? So again, because the whisker to the left was much longer than the whisker to the right, there's a possible outlier over here. All right, it just kind of says, hey, you might want to look there for an outlier. We're actually almost done. So how we just did quartiles divide the data into 4 equal parts. It gives us Q1, 2, and 3. Deciles divide the data into 10 equal parts. So we have D1, 2, 3 up to 9. All right. And then percentiles divide the data into 100 equal parts, P1 up to P99. Okay. So the octave represents the cumulative frequency distribution for SAT scores of college-bound students in a recent year. What test score represents the 80th percentile? So 80th percentile is here, and it corresponds to this. If that's 12, 14, this is 13. So this is, what is this? 1,250 approximately. 1250. So you see it here, 1250. This means that about 80% of the students had an SAT score of 1250 or less. Okay. So to find a percentile that corresponds to a specific data entry, I just don't want to talk anymore. To find a percentile that corresponds to a specific data entry X, use this formula. We have the percentile is going to be the number of entries less than X divided by the total number of entries times 100, and then round to the nearest whole number. I'm going to leave this as an exercise because I'm essentially out of time, but I think you can handle it, okay? And you have some instructions here. Oh, and let's talk about the Z-score, the standard Z-score. This represents the number of standard deviations a given value X falls from the average. So the Z-score is going to be the X value minus the average divided by the standard deviation. All right, again, that's going to be the number of standard deviations of a value falls from the average. I think you can actually handle this one as well. I'm going to leave this as an exercise. So if it's not clear, just contact me and we can talk about it. But I think I am out of time. Okay, I'm going to leave these be. I'm going to let you go through these on your own. Okay. So let me. I don't think I really wrote anything, but just in case that I did, I'm going to go ahead and load a copy of these notes. Paper. I'll go ahead and load a copy of these notes for you. So let's go ahead and share. Let's see. We want to send it to Box. Now the location. 10 spring. This is applied statistics, entire course into the notes, and we went into the handwritten section. Let me load it anyway. Something saying just load it. Okay. And we don't really need that page, nor do we need this page. Okay. So I'll send a copy. So I don't really remember if I wrote anything or not, but in off chance that I did, I'm going to go ahead and load a copy. Once this bar that you see on the screen finishes loading, as my students, you actually have a copy of anything that you saw me write. And you should already have a copy of the PDF that you saw me working through, okay? So again, once this bar finishes loading, you'll have a copy. So while we're waiting for this to finish, so keep in mind, again, exam 1 over chapter 1 is open on Pearson. It is due this Saturday, which is tomorrow by 11:59. You get unlimited attempts until it locks out. You can actually take it beyond, for all the assignments that are on Pearson, you can actually submit them past the due date, but there'll be a penalty. For quizzes, I think for homework and quizzes, the highest you can make on those is 80%, right? And then for exams, if you submit them after the deadline, the highest you can make is 79, which is a C, right? A high C, but the highest you can make is a C. I don't want you, because those are heavy weights, so I don't want you to just try to wait to the last minute and submit all that stuff and then, try to skate by. So I did that intentionally, okay? But those assignments are there. The best thing is just to get them submitted. Get her done, right? Get her done, okay? Hopefully everyone is staying healthy, keeping their mind right. I know the school is what it is. You have to do your best, okay? Keep in mind that powers that be don't want us to educate ourselves, right? They want us to be intimidated by education, deaf, dumb, confused, scared, not really pushing. This is what what the powers that be will want. I mean, that's at least that's how I feel. I can't really speak for them, but that's just how I feel about it. So don't let this stuff stop you. I say that to encourage you, like, hey, we have to take charge of our experience. I mean, we can keep making excuses and that's fine, but excuses build monuments of nothingness and they're tools of the incompetent. So if we really want to take charge of our reality, we have to take charge. And so that means that we have to do our work. We have to do it as best we can. Get it submitted, get it done, and do your best, okay? And whatever happens, know that ultimately it's okay. It really is okay. I don't want you to be stressed out about it. I just want you to do your best. Do your best, do your best, forget the rest, don't stress and be blessed, okay? So on that note, we're going to end the session here, and from one beautiful mind to another, enjoy the rest of your day. Peace. All right.